Purpose of this video is to demonstrate three tasks related to probability and how you can use Excel to complete these tasks and to build a better understanding of certain probability concepts. So the first thing we're going to do, we're going to make and use a contingency table. Then we're going to calculate expected values. And finally, we're going to show how you can update prior beliefs using Bayesian updating based on Bayes' theorem. So our first task is to make and use a contingency table. So a contingency table uh, shows how two different categorical variables are related by showing either the frequency or the probability of each possible joint event. So in this case, what I have here is two different investments. So each investment could possibly succeed or could possibly fail. Right? And what we have in the center of the table in these four cells is the probability of each of those states happening. So there's a 39% probability that both of the investments succeed. There's a 23% probability that investment two will succeed, but investment one will fail. There's a 4% probability that investment one will succeed while investment two fails. And there's a 34% probability that both of them fail. Now, the first thing we can do is we can also arrive at totals, right? So we find out that overall there's a 43% chance that investment one succeeds, simply adding across that row. There's a 57% chance that investment one would fail, simply adding across that row. And then looking at investment two, we can add together the succeed column, and we find out the total probability that investment two will succeed is 62%, while the probability of its failure is 38%. Now, where contingency tables are really useful is calculating what we call conditional probabilities. So conditional probability tells us the probability of one event happening given that another event happens. So for example, what is the probability that investment one succeeds given that investment two succeeds? Well, the way we can find that is by looking at the table up here. So what do we have? Investment two succeeds. Right? So we know that this is true, which means we don't have to worry about any other possibilities. Right? So we're just looking at this column. So the probability then that investment one succeeds is 39% divided by that 62%, that is the total probability that investment two succeeds. So put another way, the probability of investment one succeeding, so investment one success, given, we usually a vertical line to indicate that investment two success is equal to the probability that both succeed divided by probability that investment two succeeds. Right, so this is really just saying if we know that investment two has succeeded, then we don't have to worry about this other column of investment two failing. We don't have to worry about that anymore. So the question is, how much of this 62% is 39% a percentage of? And similarly, we could find what's the probability that, say, investment one fails given that investment two succeeds. Well, that would be this 0.23 divided by 0.62 here. Right? So we can find all of these different possible combinations if we wish. Now, that fact also allows us to construct a contingency table based on some facts that we might have. So I'm going to show how you can do that two different ways in Excel. Right? So one is going to be doing it logically, the other one is going to be doing it technologically. Right? That is using certain functions inside of Excel to make our lives a little bit easier here potentially. Okay, so the first thing I want to do, here's our hypothetical case. Right? We want to make a contingency table based on disease testing. Right? So we're going to think instead of just thinking of probabilities, we're going to think about, say we have a hypothetical 1,000 people. Right? And some of them will have this disease, some will not have the disease. Some of them are going to test positive for the disease, some will test negative. Now, the reality is with any disease test, there are sometimes false positives and sometimes false negatives, so we need to take that into account. So here's what I'm going to do. I'm going to make an entirely new spreadsheet here. All right, and we're going to set up our groups. So one group has the disease, the other group doesn't have the disease. And we'll look at the total here. Right. Then we have some group is going to test positive, some group is going to test negative, and then a total here. Let me adjust these columns. Just double clicking on the line in between allows the column to automatically adjust based on the entries that are in it. Okay, so what we have here, we're going to have these four different cells here. Right here in the first cell, which is B2 here, these are the true positives. That is, they test positive and they actually have the disease. False positives would be those in this cell. That is, they don't have the disease, but they still test positive. Then over here we have the false negatives, that is, they have the disease but still test negative anyway. And then the true negatives, they don't have the disease and they test negative. Now, of course, an ideal situation is that we have zeros for false positives and false negatives, but reality simply doesn't work that way. And so here's the logical path we're going to do. So we're going to fill this logically first. So we said we're going to deal with 1,000 people. So I'm going to put in the grand total here in this bottom corner of 1,000. So this is the grand total number of people. We start with that. Now we're going to have a couple assumptions we're going to add to this. So here are our assumptions. First, 10% of the population has the disease that is being tested for. Secondly, the test is what we call sensitive, but it's not very specific. Right? So sensitive means that if you have the disease, you're very likely to test positive. When we say it's not specific, though, that means that even if you don't have the disease, you're still fairly likely to test positive. So let's put some specifics on this. Let's say that 99% of the people who have the disease test positive for it. However, 20% of the people who do not have the disease will also test positive. So we have a fairly high rate of false positive results here among those who don't actually have the disease at all. All right, so let's go ahead and get some specific with some numbers. So we have 1,000 people we're dealing with. So we put that in the grand total place. Now, we also know that 10% of those people have the disease. So the total number of people that have the disease, then in my case, that would be in cell D2, is going to be 10%, so 0.1, times the grand total number of people. That'd be 1,000. There we go. So it's 100 people. Now, in order to find how many people don't have the disease, that's a matter of simple arithmetic. That is, we have 1,000 people total, 100 have the disease. So do the subtraction, which I'm having Excel do here through a formula. That way, if I want to, I can go through and I can adjust elements of this without having to go through and adjust everything by hand. Right? So if you can put formulas in to calculate something, let Excel do the calculation rather than calculate it yourself. Okay, so we've got how many people have the disease, how many people don't have the disease. The next step would be to figure out, right, of those people that have the disease, how many will test positive, right? So here we know that this test is 99% accurate for those that have the disease. That is, if you have the disease, it's a 99% chance that you're going to test positive. So up here, out of this 100 then, those that test positive, it'll be 99% of them. So 0.99 times the total number of people that have the disease. Now to find those that have the disease but test negative, it's a matter of subtraction. So we know 100 people have the disease. We subtract off the 99 that test positive. That gives us one that has a false negative. So we're getting there. The next step would be looking at that group that doesn't have the disease. How many are going to test positive? Now, thinking back, we know I said, what was it? 20%. Right, so it's not very specific, so there are quite a few false positives. So we'll put in 20%, so 0.20, or just 0.2 is also fine, times that 900. So 20% of those people that do not have the disease will still test positive for it. Right? Meanwhile, how many don't have the disease and test negative, we can find by simple subtraction. Right, so 900 people have the disease, subtract off those that test positive, the rest must test negative. Right, so to finish out our contingency table then, we are going to fill in this bottom row, which is simply a sum. Right, so we add together. So sum would also be the cell formula you can use here, the two cells above it. So B2 and B3 added together will give the total of number of people that test positive. And then I can just click and drag here in the lower right. You'll notice your cursor changes slightly. That's going to then drag and copy whatever you happen to have here. So in our case, it's a formula. So we'll drag it over and we'll use that same type of formula, but you can see to adjust the cell reference so that it's now in the C column rather than the B column. And just to double check by hand, this 1 in 721 does in fact add up the way that it should. Okay. All right. So now we have all this filled in. Now, a nice thing about this is this allows us to then answer questions like, if somebody tests positive, what is the probability they have the disease? And this is something many people get wrong, is that people hear that, oh, if you have the disease, 99% chance you're going to test positive. People try to flip that around and say, oh, well, in that case, if I test positive, it must be a 99% chance I have the disease. But here, one thing that's great about the contingency table is it makes it very clear that's not true. Right? So when you look at those people that test positive, there are 279 of them. Of them, only 99 have the disease. So it's, in fact, less than half for here. So we can actually calculate this. So the probability of those, probability that you have the disease, given that you test positive, I'm just going to put a plus sign there, right? Given that you test positive is equal to this 99 divided by this 279. Right? So that is to say, look at all the people that test positive. Of those people, only about 35% actually have the disease. We can also do the same kind of thing. Well, okay, how about what's the probability that you, say, don't have the disease given that you test negative? Right? Like, do we have the same problem there? Well, let's check. Right, so given that you test negative, oh, that should be a negative sign, not a 1. Correct that. There's the negative sign. Right, so total, we have 721 people test negative. Like, of those, 720 don't have the disease. So we can do the math. 720 divided by 721. Right. So in this case, right, if you test negative, you can be pretty sure you have a 99, basically 99.9% chance of not having the disease. And so in this case, even though we know that there are lots of false positives out there, that is exactly why you can't really trust the positive test result. On the other hand, false negatives are pretty rare, right? And therefore, a negative test result is in fact more trustworthy. And so this is something that we can do here is effectively doing it by hand using the logic of the situation we were in. Now we can also accomplish the same result, but using the technology available to us. So I'm going to show you how to do that. So I'm going to go ahead and copy this over into a new spreadsheet. Okay, so there we go. Paste it in, double click on the lines because I don't like not being able to see my labels. I'm going to delete this all out again. Okay, so the next thing that I'm going to do is I'm going to go ahead and just fill in numbers that I know are fake. So here are the fake numbers. The first number is going to be 1. The next number will be 1. The next number will be 1 and then 1. Then I'm going to put in formulas for all the totals. So here, total here will be 2. Total here, again, it's going to be 2. And I do the same kind of thing down here, but for the column, putting in sum. So it's that sum formula, and I'm going to drag this across. So effectively what I've just done is I've put together kind of a dummy setup, right, where we have just the number 1 put in for everybody. So it's like we have one person that tests positive has the disease, one tests negative has the disease, and so on. This obviously does not match what was described, right? But what we're going to do, we're going to use one of the tools that is inside of Excel in order to solve this problem. So in order to do this, we're going to use the solver analytical tool right here. So if you click under data, solver is something that should appear here. If it doesn't, it does actually come installed in Excel, but you may have to do some work to get it activated. So let me show you how to do that real quick. All right, so I'm going to have to expand so you can see my entire display here. There we are. All right, so where that is in your options, so you have File. In my case, I have to go under More. You might just be able to see options there, but you're going to need options. When you open options up, there's an option for add-ins. It's one of the last things in the left menu, like the next to last. And then down bottom center, it says Manage Excel Add-ins. You click on Go, and there's this list of add-ins. The last one here is Solver add-in. So if there's no check mark there, that's why it's not appearing. So go ahead and click that box until you get a check mark, and then you click OK. And that should make Solver appear. Again, it's under the Data tab. If you're working on a Mac, it is a slightly different set of instructions. I'm pretty sure, let me double check that I actually have the instructions here. So on a Mac, you would go under Data Analysis Tools, and then Solver is an option there that you can open. Okay, so now let's get back to our regularly scheduled program. Wrong. There we are. All right, so here's what we're going to do. So we filled these with numbers. What they are really doesn't matter much. I just put ones everywhere. And then we also have our sum formulas. Now what we need to do is lay out what our constraints are going to be. Right? So remember, we have 3 facts. One is that the percentage with the disease should be 10%. Second, 99% of the people with the disease should test positive. And third, 20% of those without the disease should test positive. So we're going to set up three formulas for this. I'm going to do it over here to the side of our formulas. So first, we're going to say this is the percent with disease. This will be the percent that test positive given that they have the disease. And then here will be the percent that test positive given that they don't have the disease. All right, and then I'm going to expand that out a bit. Now, here what I want to do, I want to calculate the numbers as they are now based on the fake data that I put in. Okay, so the percentage with the disease, this would be equal to the total number that have the disease divided by the total number of people. Percentage that test positive given they have the disease, be just looking at those that have the disease. So row number 2, those that test positive, so that'd be B2, divide that by the total number that have the disease, it's D2. And then here, the same kind of things as the percentage that test positive, that is B3, given they don't have the disease. So 3 would give us the row, B is the column here, and then divide that by the total in that row. Right, so you can see right now, all of these are coming through as 50%, and we know that's not true, but that is the way things are at the moment. All right, so the next thing we need to do is we want to update this so that we will actually hit the constraints we want, and that's what Solver is really good for. So I'm going to go ahead and click on Solver, and we can look at what that looks like. Okay, so when you click on Solver, it will open up another window. Here, let me show you what that window looks like here. And here we are. Zoom in a little bit for you there. All right. You can see you're setting an objective by changing certain variable cells subject to certain constraints. Right, so what I want to do, I'm going to set the objective where I want to have the total number of people. So I'm going to click here, it'll shrink that. So the total number of people to be equal to the total we want in our hypothetical. So set objective D4 to a value of, we said 1,000 people. Right, so then it is going to start changing things in the spreadsheet. Well, I have to tell it what it can change. So by changing variable cells, there we go, and then I choose those center 4. Right, so this is B2 down through C3. So now it knows it has the freedom to change those 4 cells to try to get that total, which I have stored in D4, try to get that up to 1,000. Now, as it is right now, the way that I have things set up, there are a million different ways, actually more than that, there are an infinite number of ways that it could simply find that combination. So I need to put in a few more constraints, and that is exactly what this box is for. So where it says subject to constraints, I want to add a constraint. And so one of my constraints is that I want the cell reference. Okay, so the cell reference that I want is first that percentage with the disease. I want that to be equal, not less than or equal, I want it to be exactly equal to 0.1. That is 10% have the disease. So I'll go ahead and add that. Then I'm going to add another constraint, and that is that G3, which is where I have the percent that test positive given they have the disease, we know that should be equal to 99%, so 0.99. And then I'll add one more, that is our G4. That one we know has to be equal to 0.20. Remember, 20% of the people who don't have the disease still test positive. And I'll click OK. So you can see it added in those constraints. So what we're going to do, Excel is now going to use a guess and check method to find what those 4 numbers are that would satisfy the set of constraints. That is, we want, one, the total number to now be 1,000, not just 4. We want those percentages to be 10% that have the disease, 99% test positive if they have it, 20% test positive if they don't have it. All right, so we just put all the constraints in here, and then all we have to do is click solve and give it a second, and it will come up with a solution. So I'm going to go ahead and click OK. And looking at the result here, you can see it's very, very similar to what we had in the previous case. Right, so here we're going to have to do a little bit of rounding because naturally 98.9997705. This guess and check method tries to get real close, but it's not going to be 100% on. So we do have to kind of allow for a little bit of error here. But 99 is basically what we're dealing with here. Right. Similarly, this 99.99977 really is a 100. Right. So with a little bit of rounding, we know that this is going to give us the same answer as what we had before. So, like either way, like walking through it logically or using the technology to help us, we can use this to construct a contingency table based on a few facts that we know about what those contingencies are and how they relate to each other. All right, the second task. Let's show how we can calculate expected values. So the idea of an expected value is that it's basically the same idea as a mean or an average, but instead of being applied to a sample or to a population, it's applied to a probability distribution. Right, so we have a number of different possible outcomes, each of them that has a particular probability, and we want to know what would the average result be. Right, so a case that you might see this would be something like the roll of a die. So what is the average roll on a standard six-sided die? Well, we know that there's a 1/6 chance of getting a 1, 1/6 of a 2, 1/6 of a 3, 1/6 of a 4, 1/6 of a 5, 1/6 of a 6. So what you do to find that average is you take that 1/6 probability and you multiply by the value of the outcome. So you take 1/6 times 1, 1/6 times 2, 1/6 times 3, 1/6 times 4, 1/6 times 5, 1/6 times 6, and then add it all together. The ending result would be about 3.5. So you can apply this not just to dice, but also to any time when you think there is some kind of probability distribution. Right, so here I'm going to go ahead. I have an example here that I'm going to kind of paste in to give the idea. All right, so here is an example. Let me clean this up just a touch before we start using it. All right, let's allow a little bit more width here, a little bit more width here, a little bit more width here, and here. All right. So what we have here is we're imagining, say, two different investments, investment A and investment B. And each of them has a different profile in terms of what their returns look like. So investment A, it looks like their profile is such that how they do really depends on the state of the economy, it looks like. Right? So if the economy is superb, then 30% return. If the economy is average, 10% return. If the economy is poor, you lose 20%. Meanwhile, investment B has a much different result in that it's going to return 30% the grand majority of the time. When it doesn't, most of the time it's going to return nothing. But then there's that really rare case. You can see here the probability of this happening is 5%, where it's just going to lose everything. Everything's gone. So it'd be interesting to compare these two investments and say, well, what are they like compared to each other? Right, so to find the expected value, what we need to do is take for each investment and then calculate probability times the return in that particular state, and then sum that all up. And that would be our expected return. So let's go ahead and do this. I'll do first for, say, investment A. So I'm making an investment A column here. This is just where I'm going to be doing some calculations. The calculation that I want to do here, I'm just going to do P times R, so that is the probability times the return. It just keeps adding a row, or widening the row. All right, and then I'm going to do the same thing for investment B over here. There we go. So in this case, I take the probability of that state. So there's a 20% chance of having a superb economy or state of the market, multiply that by investment A's return. There we go. All right, and then I will just copy this down like so. Right, so each of these is one of the terms that is going to go into our expected value. So the expected value, remember, is the sum of probability times value. In this case, the value would be the return. Right, so what I need to do is sum all of those up. So equals sum. And there we go. So we just found what the expected return is going to be. So this would be the expected value. And this is for investment A. I'm going to justify that. So there's our expected value for investment A. Then we do the same thing for investment B. Probability times return. Right. Copy this down. Right. And then again, we're going to do the sum. So I'm just going to copy that over from the previous column. So here we have the expected value in each case, right, and we've shown how we can calculate it. So in this case, it looks like investment B, even though it does have that small probability of things going really, really badly, it does have overall a slightly higher expected value. Another thing we could do here is we can compare that expected value with the median. Right, so the median, is the middle value. Now, it's not immediately obvious when you're dealing with probabilities like this, with this type of probability distribution, where the median would be. But the median is always going to be like where you have 50% of the time you're that good or worse, 50% of the time you're that good or better. Right? So you can imagine kind of moving in from the edges and say, well, what's in the center? So, or were you crossing kind of that 0.5? So let's do that. So what we can see right here, if we start at the top, right, so you have 0.2. So if we imagine, say, a line segment of length 1, so we start at 0, it goes up through 1. So we're going along, we start at 0, we go up to 0.2, right, so we're not quite to 0.5 yet. So that would be the superb range, is from 0 to 0.2. The great range would then be from 0.2 to another 0.25, so it'd be to 0.45. Right, so we're getting close, we're still not to 0.5. Right? And then good would be from 0.45 up to 0.7. Okay, so we just found it. So the good state of the economy is what will be at that 50% mark. So that 0.5 is going to be within the good range. So that means then the median return here for investment A is 15, which is really, really close to the expected value. So in this case, the median and the expected value are very similar to each other, which means most of the time this investment is going to return right around the average. On the other hand, investment B is very different in that its median return is actually almost twice as big as its expected value, which means that this return, if you look at history over short periods, is going to look really, really good compared to its actual return over a very long period of time when you take into account that occasionally the economy is poor. And so the fact that it has this really unbalanced return means then that over short periods, things are going to look much better. Say most of the time, this looks like a better investment over short periods. But when you look at the average over the long run, it still does outperform, but it's not by very much. And so this would be another thing that we can do with Excel fairly easily. All you need is probabilities, and then what are the values attached to those probabilities, and you can calculate expected values this way. The last task that I want to show you is how you can update prior beliefs using Bayes' theorem. Okay. Right, so the basic formula here is, so Bayes' theorem tells us how we can take and we can flip the conditionality of a conditional probability. Right, so say using the example from before, what is the probability that somebody is actually sick, that is, they have a disease, given that they tested positive? That's something that is not immediately obvious from knowing probability you test positive given you have the disease. So Bayes was a great person in the world of probability theory, and he came up with a rather simple equation for how you can find this. Right? And so that equation, I'll just go ahead and type it up here real quick. It says the probability of B given A is equal to the probability of A given B times the probability of B divided by the probability of A. Right? So if you know all of those elements, probability of A given B, probability of B, and the probability of A, then you can calculate and flip that conditionality. So you can find the probability of B given A. This is also sometimes used to update our priors based on new evidence. So we have within ourselves, right, various theories about how the world works, and we update these theories based on encountering data. Right? So applying this, all we do is take that same formula and replace B with theory and A with data. So the idea here is we're going to say the probability of a particular theory being true, given the data that we've experienced, is equal to the probability of the data happening according to that theory. That is, if that theory is true, right, multiply that by the probability of the theory being true in the first place, divide that probability of the data occurring. So what you do here, the idea is that you have multiple theories of how the world can work, and then each of these theories you attach a probability to. Each of these theories also suggests some probability of whatever the data we might possibly observe. What is the probability of it actually happening? Right? So if we know the probability of the actual data given the theory, know the probability we've attached to that theory based on our own prior beliefs, and know the overall probability of this data happening regardless which theory is true, then we can use this formula to calculate what is the probability of that particular theory being true given the data. Now, this sounds real weird a lot of the time to people, so let me lay things out and then we'll work through a specific example. So first, how do we do this in Excel? So I'm going to go ahead and take these. I'm just going to pull them off to the side so we can refer to them if we wish. All right, so I'm going to first just lay out the basic format. All right, so we have various theories. I'm just going to call them A, B, and C. We have prior probabilities. I'm just going to call those probability 1, probability 2, and probability 3. We have the probability of the data given the theory, and this is something that we will have to decide based on the theory itself, so x1, x2, and x3. And then we'll need to calculate, for the purpose of updating, a couple other things. That is, what's the probability of the data given the theory times the probability of that theory being true. So this would be that numerator. So if I look at my formula again, the numerator here is probability of the data given the theory times the probability of the theory. Well, I've already put both of those elements in. So this one I can actually calculate based on the data we have, based on what we've already input. So this would be B2 times C2. Okay. Right now, those are not values that Excel can work with. So it's just going to give me an error saying value because x1 isn't actually a number. Then we also need to know what is the total probability of the data. That would be our denominator down here. Well, good news. We have the probability of the data given the theory 1, theory 2, and theory 3. Now I know one of these has to be true, so if we add these all together, that would give me the total probability that the data is going to be observed. I'm going to put some bolds in here. Right, so equal is just the sum of these three things. All right, once we have that, we'll have all of the elements we need to be able to calculate the probability of the theory given the data. So remember, so all we need here, we need that numerator, which we calculated in column D in this row, divide that by the denominator is that probability, total probability of the data happening. So in my case, it would be D5. Okay, and then enter. All right, now here I want to make sure that D5 copies down without change, so I'm going to put $signs in there. That makes it an absolute cell reference, and then copy it down. So now all of my formulas are correct. So D2, this should update to D3 and D4. Excellent. So everything's looking like we want. All right. So how do we actually use this thing? Well, here's a hypothetical case. So suppose that I have a bag of dice. And as somebody who does in fact play Dungeons and Dragons, I currently DM for my children occasionally, right, I do in fact have bags, boxes, etc., right, filled with dice with different numbers of sides. Right, so some of these dice are four-sided, that is, they have the numbers 1, 2, 3, and 4 on them. Some are standard six-sided dice, numbered 1 through 6. Some are eight-sided, they would be numbered 1 through 8. Some are 10-sided, numbered 1 through 10. Some are 12-sided, numbered 1 through 12. Really cool die, by the way. And some, most commonly used in Dungeons and Dragons, being the 20-sided die, which is numbered 1 through 20. Right? So let's just say that without any other information, you think I probably have equal amounts of these dice. So if I randomly pull one out, you think each of them is equally possible. So what we now have is 6 different theories. So I'm going to adjust this a little bit based on that. Right? So I'm going to have to pull this down, make room for the additional theories. So we have these 6 theories. So one is that it's a 4-sided die. One is that it's a 6-sided die. One is that it's an 8-sided die. One is that it's 10-sided, 12-sided, and then 20-sided. And we also have our prior probabilities. You think each of these possibilities is equally likely. That is, there's a 1/6 chance of it. So it equals 1 divided by 6, and then I'll just copy that down. Right, so each of these, before you know anything about this, if I just pull out one die at random, you think it's equally probable it could be any of these. Now let's suppose that I do that. I pull this die out. I'm not going to show it to you. I will just tell you what I roll. So I roll the die, and it comes up a 10. Right? Now I want you to figure out what the probability is that it is each of these potential dice. So how do we do that? Well, we need to finish filling out this formula, right? So it came up a 10, so that's our data. So what is the probability of rolling a 10 on a 4-sided die? With each of these, I'm going to pause for a second. You can think about it. what the answer would be, I'll just move forward. So four-sided die is numbered 1, 2, 3, and 4. You're not going to roll a 10 on it, so the probability of this happening is exactly 0. Now, next one. So what is the probability of rolling a 10 on a six-sided die? Still 0. What's the probability of rolling a 10 on an eight-sided die? Still 0. So in each of these cases, right, we can effectively rule out that theory, and that is what is happening here on the screen, actually. Can't see it just yet, but it'll be obvious in a minute. Right? Is that we're saying, according to this theory, if this theory were true, if what I pulled out was a four-sided die, then the data we observed, that is, the 10 being rolled, is impossible. Now let's look at the ones where it is possible. So if I have a 10-sided die and I roll it, there's a 1 in 10 chance it's the 10 that comes up. So in that case, the probability of the data given the theory is 1 divided by 10. That is 1 because one side has a 10 on it, divided by 10, the total number of sides available. 12-sided die is the same idea. Right? So there's a 10 on there. There's one chance that I could roll a 10 out of the 12 possibilities. So 1 divided by 12. And then on a 20-sided die, again, there's one 10 on there out of the 20 possibilities. So 1 divided by 20 would give us probability of the data given the theory in that case. Now I have to copy this formula down here. Right. Also need to update this one because the sum should actually be for all of the possible theories. So I need to update this. It's not D4 anymore. This needs to go all the way down to include the next 3 lines as well. So it's D2 through D7, and there we are. Now that last column, again, I'm going to have to drag this down. I want to make sure that it's referring to D8 here rather than still D5, and it is, so we're good. So this is now what we call our updated beliefs. That is, what is the probability that I pulled out a four-sided die, given that I rolled a 10? Also not possible. What's the probability that I pulled out a six-sided die? Still not possible. Eight-sided die? Also not possible. Now it's the probability that it was a 10-sided die. Now notice here, it wasn't just that now each of these three is equally likely now. Instead, what we do is we count for the fact that rolling a 10 on a 10-sided die is more likely than rolling a 10 on a 20-sided die. So adjusting for that, we now find that the most likely die for me to have pulled out is in fact the 10-sided die. Now it's still a less than 50% chance, but nonetheless, I calculate and find, oh, well, it's actually more likely that it's 10-sided than anything else. We can also then actually go through other rounds of this if we wish. Right, so for example, I could say, well, what's the probability of rolling a 10 again? This is something that we could do. And one way we can do this is say, well, since we have a new set of probabilities for this theory, for our theories, what we can do is copy this over, right, into our prior probabilities. So I rolled that die, it came up a 10. Now we can adjust our beliefs. That's exactly what happens here. So I'm going to go ahead and copy that over. Oh, I see. It's complaining because there's a circular reference. I need to copy in, not this. Okay, let's try this again. Copy, and I need to paste values. Yeah, it's big pain about this. All right. Let me undo. Okay, paste values. There we go. All right. And then what I can do and find, okay, so this would be my prior probabilities given, right, that I've already observed a 10. So I take that same die. What's the odds that I'm going to roll a 10 on it again? Right? And that is what this calculation tells me now. Right? So these are all the different probabilities of rolling a 10 on that die. Putting it all together, this is the probability of rolling a 10 right now, right, given that I know that I rolled a 10 before. Notice this is much higher than it previously was. And then if it happens again, then notice that's going to change our probabilities again. If I just keep rolling a 10, then we're going to start thinking, well, maybe this is a 10-sided die. Also, maybe it's not a fair die. I haven't counted for that possibility here. But this is something we can do, right? This type of Bayesian updating is something that is kind of tricky for a lot of people, right? But is something that we can, in fact, work through using Excel. Another kind of classic case of this would be the Monty Hall problem. So let me go ahead and share that one with you. Right, so the idea is this. Okay, so I'm going to go ahead and copy this over, right, and we will certainly be adjusting this. Right, so this was based on a TV show, a game show called Let's Make a Deal. And at the end of this show, you had the contestant there, and they had three doors that they could choose between. Now, behind these doors, one of them has a car, two of them have a goat, right? And the goat is effectively you've lost the game, right? And so, I guess if you really want a goat, that might not be losing. But so one car, two goats. So I want to know what the right strategy is to approach this game. And here are the rules, right? So you'll pick one of the uh, doors. After you pick a door, Monty Hall, who's the host of the show, is going to open one of the other doors. Now, the rule is that Monty will never open a door to reveal a car. He will also never open the door that you've chosen. Now, after he opens the door, you then have the opportunity to switch, right, and choose the other door. Okay, so let's work through this. Right, so our theories are this. Right, so our theories are we have, let's just call them A, B, and C. So A has the car, B has the car, and C has the car. And then I'm going to eliminate the extraneous rows that I don't need anymore. Delete. So our sensible prior probabilities is that these would all be equal. I'm just going to put 1/3. Okay. All right. So it's a 1/3 chances behind any of these doors. And now let's say that I choose door A when I first. So I say, door A, that's my door. So I'm going to say this one's chosen. Then what happens is that Monty Hall opens door B, revealing a goat. So Monty Hall opens B, revealing a goat. So here's the question. What is the probability that Monty Hall would open door B, revealing a goat there in each possible case? Right? So let's suppose that that car is behind the door that I chose. In that case, Monty Hall could open either of the other doors. They both have goats, so pretty much it's a coin flip as to which of the other two he will open. So that means then the probability of him opening B, revealing a goat there, is 50%. It's 50% he could have chosen B, 50% he could have chosen C. Either one would be allowed by the rules. So the probability of the data that we see, that is Monty Hall opening door B, revealing a goat there, is 0.5. Now, what's the probability of him opening B, revealing a goat there, if B had a car behind it? Well, that's obviously impossible. If in fact B has a car behind it, Monty Hall can't open door B by the rules. So the probability of him opening B to reveal a goat, if in fact there's a car behind door B, is 0. The last one is, what if the car is behind door C? So in that case, if that is true, remember Monty Hall will not open the door that I've chosen, and he will not open the door with a car. That forces him to open door B, revealing the goat. So in this case, if that is true, given all the scenario, it's certain that he would open B, revealing a goat. So in the case that the car is behind door C and I've chosen A, he has to open B to reveal a goat. So that'd be a probability of 1. So now let's look at what this says. So this tells me then that after I do all of my Bayesian updating, I would find out that after that opening of the door B, there's now a 1/3 chance car is behind door A, but a 2/3 chance it's behind door C, which means the best strategy, you're going to win twice as often if you switch and choose whatever door he didn't open that he could have. So that would be the solution here to the Monty Hall problem, right? Again, right, solved using Excel tools.